my talk is also in the constructive setting, so it's about computing solutions of ordinary differential equations in Rocq. And so what exactly am I going to talk about? So the problem we consider is so initial value problems for autonomous ordinary differential, first-order differential equations like this. So by the function, and the time derivative is given by the value of the by f of y of t, and you are given an initial value at time 0. Right? So, well, why is this problem interesting? Well, it is a very classical problem in analysis. It's widely used in applications, for example, in dynamical systems. There's also many safety-critical applications in engineering and so on. So it's an interesting problem for formalization. Well, it's usually used. The way it is solved is the way that we study the dynamics is usually using numerical approximations, because so for most interesting initial value problems, there's no closed form solution in terms of like elementary functions. So usually numerical methods are used to study the dynamics of the solution. Well, why this specific form? Well, so this is not so much a restriction. So, for example, we look at autonomous systems, but of course you can always, if you want a system that also depends on time, you can always introduce a variable for the time. So you can always make it non-autonomous. And also if you want higher order derivatives, you can introduce variables for the higher derivatives and reduce it to this form. Right, so this is the problem we look at, and the goal of this work is okay, so maybe I should switch to this. Okay, so works very, yeah. Okay. So the goal is to develop a method for computing solutions of initial value problems. Well, for a suitable class of right-hand side functions, I will say more about this on the next slide. Of course, with formal guarantees of correctness, and inside the Rocq proof system. And here, well, I mean, the computation itself should also be inside. So it should be possible to compute, for example, so for computing values over time of the solution inside of Rocq, and output this inside the proof assistant. Okay, and so, well, I just said for a suitable class of function, and what is the class of functions that we look at? Well, we will look at only at analytic ODEs, so only for the right-hand side being analytic. Right, so, well, first, well, if we have general ODEs, then computation might not be possible, because first, without any assumptions, well, there might not even be a unique solution, so there might be no solution or infinitely many, and they might not be computable. Well, in numerical methods, well, for most, so, well, if we have a unique solution, then, well, it's computable, but still, usually we assume a bit more. So for numerical methods, many methods at least assume that the right-hand side function is Lipschitz continuous. But if we want more efficient methods, then usually also a bit more smoothness, like CK for some k. For many cases, even polynomials are enough, right? Well, polynomials, so especially if we think about just doing numerical computations, then so many non-polynomial ODEs can be transformed into a polynomial form, again by introducing additional variables, right? So, for example, here we have a very complicated ODE, like so this is 1 over 1 minus e to the y, but so just introducing variables for e to the y and 1 over 1 over 1 minus v. Well, if you compute the derivatives using what you learned in elementary school, then you can see that the value you get an equivalent ODE in the sense that well, so you have 3 variables now, but the first one will give you the solution of the original problem. Right, so yeah, so this works in this example, and it also works for so for all elementary functions and many other functions, you can just kind of mechanically transform it to a polynomial system. And even if you don't have such an explicit transformation, then often in numerics you often work with something like Taylor models or other polynomial approximations. So you operate on polynomial approximations. Well, we kind of focus on, we could focus on polynomial initial value problems, but polynomial, so the solution of a polynomial ODE is in most cases not polynomial, so usually not polynomial, except for trivial cases. The theory for polynomial ODEs is kind of nicely generalizes to analytic ODEs, which have then also an analytic solution. So we focus on the analytic initial value problems. So what a right-hand side function is analytic. Right, and so what did we implement in Coq? So as I said, this is also in the context of constructive mathematics and constructive analysis. So we formalized the constructive proof of existence of uniqueness of the analytic solution. Right, and so what do I mean here by constructive? So first, this is in the context of constructive reals. So basically, so when we so the real numbers are basically given by a representation something equivalent to this. So we have a sequence of rationals which approximate the real number, and we have an effective modulus of convergence. So we know how we can compute how fast this approximates the limit. Right, and there is already an implementation, so constructive reals are formalized in the Rocq standard library already. There's an interface for constructive reals which can be implemented with different types of representations. But the one that is implemented in the standard library is called the constructive Cauchy reals, where you basically use the standard rational type, the type Q, for your approximations, and there's, for example, if you want to output, so you can write sec x and an integer, which will then give you a rational approximation of x with error bounded by 2 to the z. Right? So if this is, for example, -3, it will give you a -3 approximations. Right? So this is about the real numbers, and so I will say more about what I mean by computing the solution soon. But so first, the mathematical background for this, for analytic initial value problems, is the Cauchy-Kovalevskaya theorem, so a very classical theorem in mathematics. So basically, the Cauchy-Kovalevskaya theorem is the theorem that says the solution of an analytic initial value problem is again analytic. Right? So here we mean we are looking at multivariate analytic functions, so given locally by their convergent power series expansion, so by their Taylor series, in a neighborhood of the of points in the domain. And the Cauchy-Kovalevskaya theorem says that if a function is analytic in a neighborhood of the initial value, then the solution will again be analytic on some small interval around 0. Right? So. Okay, and so actually the formal proof is very similar to the classical proof of the Cauchy-Kovalevskaya theorem. So it's a very nice 19th century mathematics. So the main idea, so this is the same for the classical proof and for the formalized proof. The main idea is proceeding in 2 steps. So the first one is giving the solution as a power series, so a formal power series of the solution. So when we are given the power series of the right-hand side function, of this function f, then we can so basically just using the chain rule. So if we know what, so we know the initial, we know what the value at 0 is, then we see what the first derivative is at f of y0, and so on. We can then use the chain rule to get an expression of higher order derivatives of y, and from this we can get kind of a recursion for the power series coefficients of so this should the power series coefficients, the coefficients of the power series of y at time t0. Right, and the second part, so this will just give you a formal power series, and you also have to show that this power series converges. So the second part is to show that this series converges. And so the classical proof then proceeds by saying that, well, if this is if the right-hand side is a convergent series, we can bound it by a simpler series. There's So we can bound it by a simple majorant ODE. And from this majorant ODE, we can get a majorant ODE for the solution, which then shows that this has a positive radius of convergence. Right, and so here, here's one problem is that the classical proof. So this step, especially the second step, is it's not constructive. So there's no way to compute the majorant from the power series, for example. If we want to extract computational content, we have to look a bit closer. Okay, so what do we do? The main thing here is that we have to make a bit more explicit how the right-hand side function is given. Right, so here is so here's how we kind of encode power series, converging power series. So so this is for the one-dimensional case, but this generalizes quite simply to higher dimension. Right, so if we have a power series like this, then similar to constructive real numbers, we have to kind of know how many coefficients we have to look into. So how far we have to look into the sequence to get a good approximation. Right, so we kind of need a modulus of convergence for the power series. So or some explicit convergence data, like a radius where it converges and a modulus. A convenient way to encode this information is to use the majorant bounds like are used in the classical proof of the Cauchy-Kovalevskaya theorem. Right, so we can encode this information by just two constants, so R is basically the radius, or a lower bound on the radius of convergence, and M gives you a bound on the coefficients. Right? So if we have such a bound, then we can approximate. So then for any K, we can get a tail approximation, and from this know that. So if we for example, if we choose something in the center of the radius of convergence, then we see that if we use linear, so if we use the first n coefficients or the first k coefficients, this will give a 2 to the minus k approximation of the solution. Right, and so this can also be generalized to multivariates. Okay, so what exactly did we formalize in Rocq? So first, there's a large part about formalizations of just multivariate power series in this way, majorants and so on. And as in the previous talk, so we here have a ring of power series. So all of this is using like setoid constructions and ring constructions in Rocq. The solution or the kind of theorem that we formalized is that, when we are given a formal power series at the initial value, then we can compute a formal power series for the solution, which satisfies the ODE in the sense that, derivatives in the sense of derivatives on formal power series. Right? So it's kind of an algebraic property that we have on for the derivative, so the formal power series will satisfy this. And the second part is, so we also want to show that, if the original series was converging, then the result will also be converging. Right? So if we are given a majorant pair for f, then we can compute a majorant pair for the solution y. And this will show that on a small interval, we have convergence of this power series. Okay, and so this will only give convergence on a small interval, of course. So this will only give us very small local solution. And so what we then want to do is we want to extend this to. So we want to use this initial value to the new solution to extend this to compute longer trajectories. Right, and so here again, this is a bit different from what is typically done in numerical. For numerical methods. So for numerical methods, so usually, similar methods are used, like computing the power series up to a certain point and then cutting the series, approximating the tail error. But then the error is usually reduced by making the step size. So making the step size here smaller, reducing the step size, and getting better approximations. Right. So in the method that we formalized, the error is not made smaller by decreasing the step size. The step size is kind of a constant that only depends on properties of the function, so the radius of convergence that we get for the solution. But the error is made smaller by getting more coefficients of the power series, right? So we kind of keep the steps. The steps only depend on the function, and if we want to make it more precise, then well, internally the power series will be expanded further. Right, and so why is this nice? So in this context, this is quite nice because we can kind of consider the value, for example, at this point, just as the value at this point as an exact real number that we can just give the algorithm for the local solution again. Right? So we don't really have to think about how the error propagates over time, because we kind of feed an exact real number to the local solution algorithm here, and then we can expand this. Right, and so how does it actually, so what can we actually do in Coq with this? Well, the first thing is, well, how can we define ODEs? So again, well, there's a few specific things for polynomial ODEs, because polynomial ODEs are easier to define. So there's a few. And so if we want, so for example, if we we can define ODEs just like this. So we can basically just write down the polynomial of the right-hand side function. Right? So we have here's a two-dimensional ODE. So we have P1 and P2 is defined like this, and then well, we define a tuple of those two, and then the initial value of those two. Right, and then well, we can then instantiate this with any real number type. So for example, we can use the Cauchy reals from the standard library. Right, so this is the simplest one. This is already implemented in Coq. There's a tactic which says so this is called a max step, in the sense that it will so it computes the radius of convergence of the solution, and it will give you the maximum for the maximum local step that you can make. Right? So, or maximum in the sense, well, so maximum in the sense that you need linearly many coefficients of the power series. Right? And well, then you can compute it. So for example, say, give me this with an approximation of 2 to the minus 3, and then it will give you this very readable output as rational numbers. So you will then see, well, so this is the time step that it made, and this is the solution of the 2 points. Right. So with this, there are a few minor problems. So first, well, the rational arithmetic becomes slow very quickly, because it's not very, well, this is just how it is implemented in Coq. So working with rational numbers is not very efficient. And also, well, step-by-step extension, in the sense that I said previously, is not feasible at all, because again, of the way this is, so mostly again of the way how this is implemented, so because it's not using a stream representation or anything. It's just, so if you reuse the solution, then it will, every time this function is evaluated, it will just grow very quickly. Right, and well, the last point is that the output is not very readable, so we probably don't really can see what those numbers is. Right, and so for this, there's also an extension to interval computations. So this is using the Coq interval library. So so the base type is defined using the Coq interval implementations from the Coq interval library, well, so this is now not using exact reals but intervals for the basic computations. So we get a middle point and an interval which encloses the solution. And so how we can use this is, so first we have to set a few parameters. So here the first one is for the interval library, the internal precision of the interval operations. So if we make this larger, then we have smaller roundings errors, but higher cost of higher cost for each operation. Then the order is the order of the Taylor expansion. So here we keep a fixed order of the expansion. And the step factor is the fraction of the maximum step size that we can do in each step. Right, and so with this implementation, we don't have these problems. So this first works much faster. So so for example, for the previous ODE, we can, so this will basically be output immediately. And we also get a nicer output in terms of intervals, which is now much more readable. And there's also a plugin to plot those things. So well, all the previous things was, of course, implemented completely in Rocq. The plotting, of course, is not implemented in Rocq. So the plotting here is just calling it. So there's a plugin which basically prints out, uses a Python script to print out those values. So there's a tactic. It's called plot trajectory. If you call it, it will open a window and will then step by. So you can actually see the plotting. So you can watch how the plot is generated, and it will output things like this. Okay, and well, so here, well, depending on, so this is now not using exact reals, but using intervals. So depending on how you choose your factors, at some point the error will grow, right? So for example, if you make those factors a bit smaller, you can see that the error will grow quite quickly. Okay, so I think I'm almost out of time. So maybe a bit about future work. Well, so first, the computation with constructive reals is currently quite inefficient, which is mostly due to the implementation. So it should be significantly faster if we are using a stream-based representation. And there should already be something like this implemented in the Korn library. And I tried it with this, but it didn't really get much faster, so it didn't really work. So also for the interval and in general, the approximation error is a quite huge over-approximation. So well, it should be made it can be made much more efficient by finding better error bounds. Also, well, the current implementation it was based on constructive methods, but especially for the interval thing, we don't really need to have constructive. We don't really need a constructive formalization, but we could also build on some non-constructive foundations. So, for example, could use what is already available in larger libraries like mass comp analysis. There's a few more extensions, but I think since I'm out of time, I will stop here and thank you very much.